All right. Okay. So now let's go to finite volume. We already talked a little bit of how to apply finite volume to two-dimensional spaces. So this time, let's actually work out the corresponding formula for three-dimensional spaces. Finite volume, again, only works if you have a what? If you have a conservation law, right? And the conservation law in 3D means I have a flux in x direction as a function of u. I have a flux in y direction. It might be different flux in the y direction as a derivative of y, and the flux in z direction taking derivative to z, and equal to some kind of a source term, which might also be a function of u. Okay, and it's always easier to write this equation in vector form. So I'm going to define f as a vector, as a function of u, having these three components, fx, fy, fz. So the flux is going to be a vector. And this part, the whole part of the derivative of the flux, can be written as what? Right? If you have a vector, you take the x component, if you take x derivative on the x component plus y derivative on the y component plus z derivative on the z component, what is it? What operator, what differential operator is that?
The gradient.
Well, not the gradient, actually. The gradient means you have a scalar function and you construct a vector out of that by taking derivative of the same scalar function in x direction and y direction and z direction and put these three derivatives together as a vector. That is gradient. Here we are doing something different. We are taking a vector to start with. We are taking a vector field and then take the x derivative and plus the y derivative plus the z derivative of the corresponding components. Add them together. So we are getting a scalar out of a vector field. What operator is that? Right, so we have basically partial fx, partial x, plus partial fy, partial y, plus partial fz, partial z. What is it?
Oh, divergence.
Yes, it's divergence. Usually we use a dot to distinguish the difference between a divergence and a gradient, right? So it's the divergence of the vector field f. So this whole thing is actually a divergence, which means the differential equation can be written as a du dt plus a divergence of f, of course it's a function of u, plus a source term. Okay, and in finite volume, we are not actually directly dealing with this differential form. We want to get rid of the spatial derivatives, right? Because we are looking at the volume averages. So we integrate that. We integrate the whole thing over an arbitrary volume we call omega usually. So we have the time derivative integrated over space, let's say V being volume, plus the divergence integrated over space, three-dimensional space, plus, I think I wrote S on the right-hand side, so let's keep that consistent. Is equal to the source term integrated over the same space. Okay, and again, if omega is a fixed control volume, the derivative jumps out of the integral. So we have the time derivative of the total amount of conserved stuff inside the volume, right? It's a time derivative of the total, plus a key thing here. So since we have said that this is the divergence, are you still familiar with the divergence theorem? What is the integral of a divergence inside a volume? Also known as the Gauss's theorem, right? Sometimes in physics. right? In physics, this would be like, okay, so the F here would be the electrical field or something, right? And the divergence of the electrical field is like the charge, right? And now what is the total integral? Wait, why can I see? Yeah, surface integral of the flux over the boundaries. Exactly. Good, thanks. So it's actually the divergence theorem. If you don't remember, review it, because it's actually important both in finite volume and in several flavors of finite elements. So this is integral of the surface flux, which is the normal, the outward normal. So let's say this is omega, n is the outward normal. So it's integral over the boundary. So partial omega is the boundary, okay? N is the outward normal. N dot with f ds. So it's the integral over the surface is equal to, let's keep this as s times dv. All right.